We'll talk a little bit about balance and heterogeneous systems. Before we get started, I want to note that I'm presenting the work of a student that I co-advise with Rich Fudig, Sarah Karamani. She is pretty close to graduation from her PhD. So all the work here is work that she has done. If it looks good, I have done a good job presenting it. If I miss something, then that reflects more on me than on her work. But unfortunately, Sarah couldn't be here. And we also like to acknowledge that some of our collaborators at Sandia, including Clay, help support and this work both in terms of funding and in terms of ideas and content. Okay, so we will talk about another type of heterogeneous system. When we say a DPU, a data processing unit, we really just mean a smart NIC. So that's this kind of terminology that has come to be used in the past few years. But if we look at something like a DPU in a modern system, then we have what you might consider like a traditional host node, which has some amount of memory, cache, and an XPU, whether that XPU is a CPU or a GPU, and then it's connected to some type of NIC. In the case of a smart NIC or a DPU, that sort of YPU in this picture actually has some processing capability. There can be many different variations of those. There are lots of vendors that have sort of custom inline processing or general processing type systems. Today we'll talk about the NVIDIA Bluefield because that's what we had access to. And so that is a system where you have some amount of DRAM and 8 or 16 ARM cores on the SmartNIC itself. So first question is, what do you do with these? If you look at sort of the disparity in terms of compute and bandwidth, here we're looking at the right, on the left-hand side at a 64-core AMD EPYC server CPU. On the right-hand side, an ARM-based SmartNIC, a Bluefield 3. You see there's a disparity, a big disparity in terms of the peak flops for the compute. In terms of bandwidth, it's a little bit better. The Bluefield 3 bandwidth is actually pretty high for a NIC, so it's about 2.8x. If you consider the compute that is available on the SmartNIC, then there might be something like 12 to 13% of potential co-processing power that you could use. You could figure out how to do something with it. So I won't talk about this today, but previously Sarah looked at taking an application, molecular dynamics application, MiniMD. This is a proxy for lamps, and trying to map that to the Bluefield 2 SmartNIC. As you see on the right-hand side here, you have sort of a serial process, and then you have some kind of parallel regions. The sort of insight from this work is that you would think that putting the exchange and the update of the neighbor list on the Bluefield is the right thing to do. Actually turns out that is the wrong thing to do because the Bluefield is very bad at sorting. So the key insight that Sarah came out from this work is that actually moving part of the force computation, part of the serial computation, and sort of rearranging the algorithm to make it more parallel was actually the right thing to do. So just briefly, showing some high-level results, there's a paper and a couple versions of talks that go into much more detail about this. But Sarah did a lot of studies with the Bluefield 2 and with certain host processors. Obviously, if you just ran on the host processor, your code would probably be faster. But there is an argument to be said that if you had, say, fewer CPU cores available or a smaller CPU and a SmartNIC, there is a crossover point kind of right about here, where you get similar performance for kind of a hybrid OpenMP MPI implementation. Sarah also did a lot of nice work with performance models to demonstrate, when does this actually take place? And if you change the parameters of the SmartNIC, how does that affect the performance? Okay. I'm going to move this out of the way. Okay. So Sarah's most recent work has been looking at a similar application. This is proxy app mini EM. And this is basically a proxy for solving Maxwell's equations. It's actually tied in with a library that Sandia and I think some of the other US labs work on called Mulu. And as part of this, Mini app has a setup phase, but we kind of ignore that. because we assume, okay, that's not really parallelizable. But then it has a solve phase, which, has an explicit parallel region. So it has these two subsolves, A sub h and A sub 22. These run at the same time, but they have different costs, and, because they sort of do different operations. I won't go into too much more detail than that because I am not an expert in the algebraic multigrid part of this. But if you have questions, we can find an expert, or I can just point to Clay and ask him who to ask. So, but the key takeaway is that these are parallelizable. And typically, they can be run with OpenMP, MPI, things like that. So the first question is, what's the opportunity? How does this run on normal CPU nodes? So we have two different sets of servers that we tested with. These are both with the HPC AI advisor, HPC AI cluster. I don't know. Rich will have to correct me. But one of them is an AMD EPYC system, and one of them is an Intel Xeon system. And don't know.
I think you can minimize it.
Okay.
Yeah.
Yeah.
Okay.
At least.
That's good. We do. Okay. Well, you can't see the top part of the graph, but
More.
can we hide this? Okay. Hide the. Oops. Okay. Thank you. All right. Great. Okay. So here we have on the left-hand side, we have Intel Xeon with 96 cores across two CPU sockets. And on the right-hand side, we have the same CPU with 128 cores. Cool. Okay. On the y-axis, execution time in seconds. And then on the x-axis, CPU cores. So we're just kind of understanding how the different subsolves perform on a baseline CPU. So as you can see here, as you increase the number of CPU cores, you do get speed up, about 3.1 to 3.5x, but there are varying, breakdowns in time for the different subsolves. So A22, takes more time than the A sub h subsolve in this case. Okay. So, sort of the first insight is that there is some potential for overlap. They're not perfectly overlap, but there is, say, a potential for some speed up if you were to sort of overlap those on a coprocessor and a host. Again, on the larger scale, when you look at more cores, there is also a little bit bigger potential 1.55x speed up. So we answer the first question, which is, can we parallelize this and get some potential speed up? The CPU case says yes. The next big question, if you're using something like a SmartNIC as a coprocessor, is what is the cost to move the data to and from that coprocessor, especially to, execute the subsolve there. So if we go back to our picture, we see here, we took in this case, we took the A sub h subsolve and moved that to the DPU, to the coprocessor, and we've left the other subsolve on the CPU. So now we're trying to execute these in parallel. This is all using OpenMP and MPI. I don't know that we're using any of the advanced kind of DOCA features to move data back and forth. So that might improve some of the performance. So the key question we're trying to answer is, what is the communication overhead for sort of transferring data for this particular subsolve? In the ideal case, is the maximum of both of these, and then sort of measure, okay, what is the overhead for transferring the data compared to that max execution time. So how much extra time are we adding on top of the parallel computation? Okay. So the studies from this, you see on the left-hand side, we have kind of the communication overhead percentage, and then the subsolve time, how long does the subsolve take to run? In all cases, the overhead is pretty low, it's about 4%. So this sort of indicates that there is a little bit of overhead for transferring data to the DPU, but it's not that bad. So this actually is another argument for saying, yes, we should probably move this, one of our subsolves to the coprocessor. Okay. And then the last set of experiments is, okay, let's just run a bunch of tests and see what is the benefit to actually offloading one of these subsolves. So what kind of performance improvements do we get? If you remember from previously, we said that the A sub H subsolve takes less time than the A sub 22 subsolve. Um, and there is some, a 1.4x potential speed up that we could get if we had, perfect or no overhead. So the first set of experiments that Sarah ran was using a set of CPU nodes and a set of Bluefield 2 smart NICs. And this is part of the HPC cluster. Excuse me. On the left-hand column here, we have just the results from the CPU execution. So this is sort of our baseline. So the best case result here is down at the bottom, the 32 CPU ranks, and nothing is running on the DPU. We haven't offloaded anything. So in this case, it takes 2.1 seconds to run the experiment that we were testing. At the bottom, then we looked at, okay, what if we add an increasing number of OpenMP threads on the DPU? So 0 to 8 is basically within a single SmartNIC coprocessor, and then 16 and 32 actually are pulling in other SmartNICs. I believe these nodes have 2 SmartNICs per node. So in the 4 SmartNIC case, you're actually pulling TPUs from another node. You're just not using the CPU cores from that node. So we'll get into why that's important in a second. But we have this nice heat map of all these different configurations that Sarah ran. And you can see in some cases the communication overhead, to move things to the DPU is not worth it if you're actually not getting, if the code is running much slower on the DPU. So in the case of where you're only allocating 2 OpenMP threads on a single SmartNIC, it really doesn't make a lot of sense to do that. If we look at sort of the single Bluefield 2 case, you also are still getting, a little bit of a slowdown. But say if you start to add, more Bluefield cores to the mix, then at some point you get, a speed up of 1.1 and 1.3x. Now you might say in this particular case, why would I do this? For the Bluefield T2, you probably would not. But we're about to talk about Bluefield 3 in a second, so we'll have some different results for that. Yeah. So realistically, you would not have a node that is a host and it has 4 smart nodes in it. Probably. You might. All right. Going back again, looking at the 128 core case. And here again, we have sort of the performance numbers as a heat map. We have our baseline kind of down here. And then we have, one scenario over here, which is 16 host cores and 32 DP cores where we see some speed up. Okay. Now, this is pretty weird. You would think normally you would say, okay, I just want to maximize the number of cores I have on the host and on the DPU. But why does this actually, give me speed up where the other configuration stalled? And to look at that, we'll look at sort of the breakdown of the different time. On the left-hand side here, we have the hybrid execution for 16 ranks. And then on the right-hand side, we have 32 ranks. Excuse me. So the CPU part is actually faster when you have 32 cores, as you might expect. So the A22 subsolve that's running on the CPU runs better if you put it on just the CPU. But the DPU part is actually much slower. So that's why in that case, if you sort of limit yourself to 16 CPU cores and use all the DPU cores, you get better results. The reason is that basically the CPU does a coarsening step and then it allocates work to the DPU via the A sub H subsolve. So it's actually giving the DPU too much work to do it. The performance suffers and the DPU becomes the bottleneck here. Okay, so in this particular case, kind of thinking about a heterogeneous system, you actually do better if you use fewer CPU cores and more SmartNIC cores. All right, so Bluefield 2, the difference between Bluefield 2 and Bluefield 3 is, the clock frequency is similar, but the memory bandwidth is much better, and it has 16 cores, kind of, better ARM A78 cores. Here, going back and we look at, this is I believe the EPYC CPU, and we see here that the best runtime for the CPU only baseline is when we have 32 cores rather than 64 cores. Part of that is because if you look at the graph here, we see that the A sub 22 subsolve scales in a somewhat linear fashion, whereas A sub H, when you reach 64 cores, basically it stops scaling, becomes a bottleneck. So in this case, A sub H is actually causing the CPU only implementation to perform worse the more, cores that you allocate to it. So this is actually good for us because then we can say, maybe if I distribute that work to the smart NICs, in this case we have 2 smart NICs with 16 cores and 4 smart NICs, then we can get a 1.6 and 1.7x speed up. But that seems a little weird, right? It's kind of unusual. If you go back and look at the numbers here, we see that there's sort of this overlap where the best total time comes when we have 16 host cores, and the best sort of overlap time is if you try to use everything. Part of that is because on the DPU, the A sub H subsolve actually scales much better than we expected it to. So this is a typo, that shouldn't be A sub H. But that's sort of why we see this kind of anomalous result where basically as we distribute the work and we give more of the parallel workload to these relatively fast, relatively high bandwidth BlueField 3 cores, we get better performance overall. Okay. Great. All right. Okay, so do I have 2 minutes? Okay, thank you. Okay, great. So the big takeaway is that this is a big little system. You have, some host cores, you have some SmartNIC cores that are comparable in performance, but not quite as good. But you can get speed up for these types of sort of parallel applications by considering what is the right way to balance sort of the allocation of work. So really, you're doing load balancing problem. To do this sort of automatically rather than systematically with all these, heat maps, you would really need some load balancing or scheduling type scheme. All right, very quickly, I think Sarah talked about this as well. There is an argument that is not fully formed, but I'll present it here very quickly. There's an idea too that you have added power usage from adding a smart NIC versus a regular NIC. So is that worth it, if you get a speed up? And in some cases, it turns out that, even if you don't get a great speed up, if you save power overall, then your green up, your sort of power efficiency is much greater. Okay, so if we look at a EPYC CPU, a standard NIC, which these are sort of estimates, we can't actually measure these very easily. The max TDP for a BF3 is more than 66 watts, but that was kind of our best guess effort. So let's say we add 40 watts for a BlueField. And if we look at some of our best performing test cases from the Intel Xeon server, let's just pick one of those. Then we can calculate if we add, 2 BlueFields, then, we might get, 1.5x speed up. We will use a little bit more power, 1.42x, and then we'll get a 1.06x green up. So we get a little bit more power efficiency, even though we're spending a little bit more energy here. You can also do sort of the opposite, where you say, yep, if I use half of a CPU and 1 DPU, maybe I just artificially reduce the amount of power that I'm using. So I'm not going to get as much speed up. Am I still better off? And in that case, even though you're not getting a speed up, you're saving a lot of power, so you're being a little bit more efficient. So you have some options in terms of how to trade things off. Okay. So basically, this is early work. This has not been published yet, but this is kind of all about finding balance. How to use a smart NIC with the host CPU. All right. I think I'm mostly on time. Any questions? To point out, we do have a smart NIC tutorial this afternoon if folks are around. I just wanted to say that.
Thank you.
Go ahead.
Very interesting work. I wanted to ask, so the main usage of the DPU logic is still for communication and for data that is going through the data path.
Yeah.
Here you focused on the scenario where you offload real computations that do not necessarily go through the data path and the network.
Right.
So how do you believe in this scenario? Is this a viable use case for DPUs?
Well, you're doing some communication because you're doing MPI, so you're transferring, between nodes. So you're doing some communication. Yeah, this is really is sort of a thought process of if we have all these general purpose cores on a smart NIC, and say if we're not necessarily using them for offloading collectives or some other communication, what do we do with them? In this particular scenario, the communication is sort of a small part of the application that is not handled by the general purpose cores. It's handled by the regular NIC. So then it's like, okay, we have this extra power, these extra cores and memory. What do we do with those in addition to the standard NIC capabilities? So yeah, I mean, it's kind of the argument is like, should you buy a NIC or should you buy a smart NIC? And what we're trying to figure out is there some balance where it makes sense to run these types of HPC applications on a smart NIC? Some of the early results say yes, to some extent, but it's sort of, as you can tell, it's sort of it needs a lot of work in terms of like load balancing and scheduling to be efficient at scale, I think. So
Thank you.
thanks.
Any other question? Well, if not, then thanks our speaker again.
Okay.